Hi guys, today I am going to discuss Miller 2.85 question. So in this we are given electrons with energy E which are incident on a potential barrier with V0 and the energy is greater than V0. So we should show that the fraction of electrons that are reflected from this barrier is R equals to 1 minus A by 1 plus A by whole square. So this is how the A is given. So let's get started. So in this question we are given energy E. So we will draw that line which has energy E and we will draw a wall which has a height of V0. So now we will define two regions, region 1 and region 2, and we have a potential V which is x less than 0 it's 0 and x greater than 0 it's potential V. So again let's draw it, and this is the incident electron beams. Some are reflected back and some are transmitted. So we have the Schrödinger equation, which is the total energy is equals to the potential energy plus the kinetic energy, and we will write the potential energy is V into the wave function and kinetic energy is the differential of the wave function, and E is the total energy. So in the region 1 we have two waves. So from Schrödinger equation we have the potential V is 0 for this region 1, and the Schrödinger equation becomes a simple differential equation. So we will solve this differential equation. Solution is of the form A e power ik plus B e power minus ik. So this is the first wave function in the region 1. And region 2 we have a potential V0. So this will be a little bigger equation with the potential energy term included. And now when we solve for this equation, we take the V0 on this left side and subtract it and define K2 as 2m into E V0 by h square bar. And so these two look of the same form. So we have psi 2 is C e power ik2 and D e power ik2. So we have 3 incident reflected. So no reflection in region 2, so minus e power k2 goes to 0, and now we use the boundary conditions. First we need to have psi 1 and psi 2 are the same at x equals to 0 for continuity. So at x equals to 0 we have a plus b equals to c, and now we have another equation that the wave function should also be finite and continuous at x equals to 0. So that gives us another relation, and we can cancel e power 0 as 1. So we will be left with a minus b k1 equals to c k2. So that will boil down to a simple equation. So we will use these two equations to get a, b and c. So first we have a equals to c by 2 into 1 plus k2 by k1, and b is c by 2 into 1 minus k2 by k1. So the incident flux density is given with the square of the amplitude a square, and the reflected is given with the square of the b. So we just need to take a and b. So the fraction reflected is the incident reflected by the incident. So that gives a very simple equation, and we can solve for the K2, K1. So A is nothing but E V naught by E. Thank you for watching this video. If you like the content, please click on the like button and subscribe to our channel. Also, please press the bell icon for further notifications. If you have any content that you would like to see, please do comment below.